Testing. Can you hear me? I'm just getting closer. Because I'm a stock speaker. Hi, everyone. I'm Aaron. I'm super happy to be back to Santa Cruz because this is a very special place for me. The model I've been working with was first originated here. It's called the Santa Cruz SAM. And not just that, but also the first time I was here, it was 2019. And I presented a poster on my thesis work, which is the first 4 paper of the JWST forecast series. And then I got a job at NASA Goddard. So I get to keep on working on what I do. And the next time I came back, it was 2022. I get to present the remainder of the series, which is some quasar stuff in paper 5, and then also light cones and clustering in paper 6. And then earlier this year, a paper on forecast for Roman also came out, which is nice. By the way, I got too nervous. I'm Aaron Young at NASA Goddard Space Flight Center. And in the fall, I'll be moving over to Space Telescope Science Institute for another fellowship. So 3 more years of science. It's very exciting. Okay, so third time here in Santa Cruz, also talking about the Santa Cruz SAM. This is the model that I've been working with since I was a grad student, which really is a powerful tool. It encompasses a lot of physical processes that we derive from observations or from other simulations, but we try to package them, well, Rachel packaged them into a self-coherent model. So we can use that to track how galaxies evolve in halo merger trees. But not just the stellar mass, but also other properties like cold gas or metallicity, how they can be predicted sort of in a self-coherent model self-consistently through these physical processes, and also we keep track of a number of feedback processes, like stellar feedback, like AGN feedback. So there's already an AGN model in place, and this is due to be updated in the next few years after I move to Space Telescope. Also, with the star formation history predicted with the SAM through the merger history with all these physical processes, it's interfaced with stellar SEDs so that we can predict the observable properties for galaxies like the rest frame UV properties or the observed frame infrared magnitude that's seen in your favorite instruments. One of them is JWST. Okay, so before we have JWST, we put out this series of forecast paper, which we try to use the SAM to push it out to higher redshift. And at that time, we think high redshift was 10. 10 was pretty high. And ask, how is the SAM performing? Are we able to reproduce the evolution history of observed galaxies that we learned from Hubble? And it looks like the SAM is doing pretty well. So these are UV luminosity functions with the solid line showing UV luminosity with dust and the dashed line without dust. And this is pretty encouraging because some of the original code that Rachel put in back in 1999, when she was still here, is still in the SAM and it works. So it's kind of like a miracle at that time, we thought. SAM is doing quite well. Here's the stellar mass function and the star formation rate distribution functions. And they also do reasonably well against observation available at that time. Now, we explore different models. The SAM is modular, it is fast, so we can try different star formation recipes, and we did have to configure one that works the best against observations. But the bottom line is the model is only calibrated once at redshift 0, and we don't just retune the parameters to make it work. So parameters tuned at redshift 0, the model takes care of the rest, and it reproduces the evolution at high redshift, which is great. Now, so after having seen Peter's talk, I decided to add this in to show that in the Santa Cruz SAM, we also will have predictions for the stellar to halo mass ratio as a function of redshift after redshift 10 here. And we just don't have that evolution that is needed. So from Peter's talk, we needed that evolution in the relation to explain those very massive galaxies that are observed at high redshift, at ultra-high redshift. But we just still don't understand how do we achieve that based on physics, right? Based on the physics that we know. Of course, there are things that we don't know. Now, this is probably the second time you see this plot, but you might see it again later. Who knows? There are a lot of models out here, and we try to make sense of what's going on. So I made a little comment yesterday that is not exactly appropriate, but just me talking to myself when I look at this plot. What are these models doing there? How are the physics that are included in the model affecting these predictions? And what can we learn? Because comparing model is non-trivial. All these models made very specific choices to match specific observations with very specific goals in mind when they developed this model. So the comment that more physics there are, fewer galaxies there are. overgeneralized, but not entirely false. There's a little trend in there, so that's something that we can think about. So here are updated model outputs that we put out earlier this year. It came out in April, which we used the SAM to make predictions for galaxy luminosity functions out to ultra-high redshift, now this redshift 17, with the observational constraints that are available to us at that time. So the plot is slightly updated from the archived version. I added in the luminosity functions from NGDeep and also from another work that came out after we submitted the paper. So we should resubmit this very soon. So there are a lot going on. Great data points from HST, color data point from JWST, cyan dash line from the old SAM. Old SAM meaning that it runs on EPS merger trees, not minute merger trees that we'll talk about in a bit. And the additional new results are the colored dashed lines. So to first order, I think the SAM is still doing quite well out to redshift 11-ish. But at redshift 12 to 17, we really still underpredict the number of galaxies relative to the numbers of reported observations. If we take a closer look, we can see that redshift 10, we're still on par from what people think, well, observers reported back in the number density across a wide luminosity range. But then at redshift 17, well, those sources are actually not there anymore. So that's why they're plotted in with an open circle. So let me get right in. A big obstacle for predicting galaxies with the SAM at high redshift, very, very high redshift, is that we don't really have merger trees that work. So for illustrious TNG, which we learned an incredible amount of with at lower redshift, it only has about 14 snapshots at redshift 12 and at redshift 6 and above. And for Bouchard-Planck, we have 29 snapshots at redshift 6 and above. This is not enough for constructing merger trees for a galaxy at redshift 17. VSM DPL is great. We got 62 snapshots, and they're fairly close together. We can construct reasonably well merger trees that we can use. But it started doing graph before I found VSM DPL. So I did it actually back in 2020 when I first ran this suite of simulation. 171 snapshots going from redshift 40 to 7 to 6, so that I can actually capture the halo merger history that from the very early time, from the onset of when halos start forming. Actually, this is Peter's idea, because we had the early communications where he suggested we should save one snapshot every 10th of dynamical time, which is definitely an overkill. But hey, now we actually resolve halo merger with good temporal resolution, which has been missing from a lot of past simulations. So I don't have a huge cluster. So this is a poor man version of a high-resolution simulation. It's actually 4 boxes. I can't afford to run this in one go. So the smallest box is only 5 megaparsec on the side, but it resolves halos down to 10 to the 5 solar mass. And then we gradually step up the ladder with the rest of the boxes. So we go up to 15 megaparsec on the side, 35 megaparsec on the side, and 90 megaparsec on the side. All of these boxes are just 1,000 Q particles. But what we're trying to do here is simulate, run these boxes from redshift 200 down to 6 just to capture the first episode of halo, how they emerge and how they merge. And from there, hopefully, it gives me the information so that I can graph together these merger tree branches to form a really big tree. That's why I leave it graphed, even though it's spelled wrong. It stands for gadget at ultra-high redshift with extra fine time steps. I do want to say that we have an amazing pre-doctoral student, Sri Nguyen from MIT, who worked with me for the past year, with us for the past year, and to train a neural network to build merger trees. So to something that we can replace extended price structure formalism to build merger trees that are actually informed by n-body simulations and also informed by these very high-resolution trees. So the ICMM proceeding was already out, and the actual paper that we have submitted to MNRAS will be out on Thursday morning. So I won't be here, but check it out. This is really cool. Right, so back to these predictions. Now we can see that a lot of obstacle that we have in the past is not just from physics, but also from not from galaxy formation physics, but from the underlying halo merger trees. They just weren't good enough for redshift 17. So by swapping out those trees for the new trees from the graph boxes, so on the plot we go from the cyan dash line to the color dash line, we already see that we have a lot more galaxies just when we capture the merger activities properly, and capture the halo mass function properly. So that's already a big leg up, and looking forward to run the SAM on the new Flora tree, the machine learning trees. So, that would be great. I want to say that these data points are no longer here. Okay, so to answer the questions, are Redshift 10 and above galaxies surprising? I zoom into these Redshift 11 and 13 panels, and let's take a quick look. So there are a few things that we talked about yesterday, but here are a few things that I was thinking when I wrote this paper. So things that are underreported. I think one of the very important things is cosmic variance. So we have to remind ourselves that these early JWST observations, especially was within the first year, Sears got half the epoch, and then a lot of the fields are still being developed, and the luminosity functions measurements are already coming out. And we just underlooked that the cosmic variance from these very small fields can be very, very big, and not all of them are folded into the error bars reported. So we tried to add the error bar back into these observations. So we had two cosmic variance calculator, one showing with the magenta bar, one showing the blue bar. And if we add that to the, let's say, yellow point on the left panel, then we get the error bar that is shown by the gray bar. So the error bar can be a lot bigger if we fold in cosmic variance. That's one thing. Another thing is redshift uncertainty. So you can see because there are only very few sources, so we have to bin galaxies across a very wide redshift bin. So some of the bins going all the way from redshift 9.5 to 12. So up there I show you the luminosity function at redshift 9 and the luminosity function for galaxies at redshift 12. And you can see that, yes, it spans a wide range. So if your galaxy in that bin are mostly redshift 9, then yes, the line is going to be higher. But a lot of people think that, okay, this is a wide bin. Let's take the median of the bin. So redshift 11, right there. So that's something to keep in mind. The range is going to be big. Okay, top-heavy IMF. Let's say galaxies are just brighter because the IMF is top-heavy. So let's say we make it twice as bright. So we shift the curve to the right. And then we're already getting closer to where the points are reported. We get 3 times brighter or 10 times brighter. So we are all the way in there. It's just throwing up possibilities out there, Not saying that the IMF is really doing that, but just saying that this is what it takes to explain what's going on. So these are just a few examples for what could explain the redshift 10 and above galaxies. But going to, just looking at the scaling relations, I'm not too worried about what the SAM is predicting because so far nothing catastrophic there. Right, so next time when you look at this figure, now you know. There's still a lot of things that we don't currently know, and physical processes has to be implemented, but the discrepancy might not be as big as advertised. Okay, so a few more things that we ask ourselves. Now we turn around, instead of using the SAM as a prediction tool, we can use the SAM as a diagnostic tool. So a few questions we ask ourselves. Are there not enough halos? The answer is no. And Joel brought up this point earlier. We should all stop using Sheff and Torman in 2002. Because even though with the updated cosmological parameters, the Sheff and Torman parameterization is still about 20-30% lower than what a native Planck cosmology simulation would predict. So it's about 20-30%. But the discrepancy go wider and wider as we go out to higher and higher redshift. So use something else. Maybe use graphs. Okay, so is gas not cooling? So we looked at the SAM and we compared the gas cooling rate to the halo accretion rate. And we found that at least in the context of the SAM, the gas is cooling as fast as the halo accrete mass. So there are cold gas. We can form stars out of it. So it's not that we don't have cold gas in the context of the SAM. Okay, so is it inefficient star formation? Now we ask the question, are those cold gas getting turned into star? So we plot the gas depletion time, blue for H2 and then red for cold gas. In our model, we use H2 as a tracer for star formation rate, but then it's still forming star out of cold gas. So the gas depletion time is a lot shorter than the age of the universe, which means that there is enough time for this gas to turn into stars. So it's not that they're not forming stars. There's time. So what we found is that in the context of the SAM, the current feedback model is kicking gas out, ejecting gas too efficiently, so that the gas outflow rate is almost comparable to the halo accretion rate. So as quickly as halo accrete mass, the SAM is also use stellar feedback to kick the gas back out. So that's why we're not forming stars at those early times. So I guess we should go to coffee and come back to listen to Avishai's talk. All right, I'm done. Thank you.
Peter.
I'm just wondering about, great talk by the way, I'm just wondering quickly about the top-heavy IMF, because if you put more of the mass into massive stars, you also get more feedback. So wouldn't that actually cancel things out and you wouldn't necessarily get a brighter set of systems?
Right. So again, SAM is great because it's at least physical. We can track these things and we can, it's fast, it's modular. So yes, again, we can think about what is important, but ultimately we should fold this all in and see how these different parts play with each other. So yes, that's that.
Any questions, David? Anyone else?
With your recent updates, is there anything significantly added to the dust component? Because dust at early times, I don't know what you had modeled before, but I can imagine that being quite different today than it was, say, 20 years ago.
So not yet. It's the same dust model. So it's just a dust attenuation model that scaled with metallicity and surface density of cold gas. But what we also found is that with our current model, we don't need a lot of dust at redshift 10 and above. So before we can make more galaxies, let's not put dust in.
Richard, do you have a...
Just wondering about stochastic star formation. I guess you can't force everything to be on the main sequence, but if you did you look at the impact that if there's huge amounts of scatter? But maybe you can't force that into your model. It's not natural.
I mean, we just have to find a way to implement that, right? Because we get to follow the evolution history of a galaxy through the merger tree. So we can find ways to do that. So in the past, we found that increasing stellar feedback actually do increase the burstiness of a galaxy. So, that's one way that is relevant and we can test out.
Yeah. Well, anyway, it could be. Well, there's many different mechanisms people have been discussing. So it would be
try them all.
Nice to try them and see how they work in the context of your models.
Add that so far a lot of papers we saw are recycling old models and poke them and see what could go wrong or could be changed. But I hope that in the next year or so, a lot of new models developed to try to fit these constraints will gradually be released.
In the luminosity function plot, it seems your model is lower than observation at redshift 11 and 12. What's your explanation for that?
It's like a few slides for that, sure. So these are the explanations, perhaps. I don't know. It's lower because stellar feedback is strong, so really the models are not forming star as quickly as the observation hints to. So we'll see. We'll have to try a lot of things in the future. So actually, the backup slides, I'm not going to go through them, but it's really, we have to go back to what we did for the first two papers in the forecast series. We actually tried a range of model configuration and asked what is actually permitted by these observations. What is the range of observations, well, the range of parameter space that is still permitted, not ruled out by existing observations. So we have not done that yet, but once I think we have a few interesting enough physical models included in the SAM framework, and we can use that to explore, what is the likely scenario that help reproduce the evolution out to redshift 17.
All right, so let's thank Aaron and the speakers of this first half session, and let's go for coffee.